Greetings everyone, welcome back to General Chemistry. Today we're going to be looking at the topic of electrochemistry, which might also be a shorter video than average, just like our thermodynamics video, but we'll see how it turns out. So I would like to start by showing you something I discovered in my drawer a couple months ago. So while I was going through my stuff, I found this old pack of batteries that I didn't use, and well, as you can see, this is what happens to batteries when you don't use them for a while. So I'm not going to go into the details of why this happens, but batteries are directly related to what we're going to be talking about today. So yeah, I held on to these for a few months just for the sake of showing them off in this video. And after I'm done recording, these are going to the trash. It says that they're guaranteed for 10 years. I just noticed this. And I know I've had these batteries for less than 10 years, so I don't know. Maybe I can sue Duracell, but it's probably not worth it. Okay, so little battery thing aside, let's go ahead and talk about how we can create a battery. The battery we're going to show is a bit bulkier than, the batteries that we're used to using. But yeah, let's go ahead and put this thing together. So, in electrochemistry, you're going to need to understand what an electrochemical cell is. It can also be called a voltaic cell or a galvanic cell. So let's see, voltaic, electrochemical, or galvanic cell. All three of those terms are used. And as for my personal preference, I don't have one. But I think I usually go for voltaic or galvanic because it's easier to pronounce. It's not a mouthful. Okay, so for our example, let's say we've got a bar of copper over here. So this is a bar of copper metal. And I guess I'll emphasize that it's solid. And it's dipped in a solution of, I don't know, let's do copper 2 chloride. So it's going to contain copper ions and chloride ions. And let's say that over here we've got a bar of, let's make it silver. Over here we'll have a bar of silver. And it's going to be dipped in a solution of silver nitrate. So you'll have silver ions and nitrate ions inside here. Okay, and we can connect both of those metal bars by some wire to a device that we wish to power. Or typically what we'll have here is a voltmeter to measure how much voltage we get across these two compartments, these two half cells as they're called. But yeah, you can have a device here or voltmeter for the electricity to go through. Device or voltmeter. And so, based on chemical reactivity, whichever one is more reactive is going to start dissolving, and whichever one is less reactive is going to have the ions in the solution start I guess precipitating would be an appropriate word, but it's not really precipitation. Well, the ions would start depositing on the metal bar. I guess you could call that precipitation, but I don't know if it technically fits the definition. So in this case, I happen to know that copper has more chemical reactivity than silver. Generally, the metals used in jewelry have really, really low activity. So I know that copper will ionize. So we're going to get solid copper is going to turn into a copper ion, Cu2+, plus 2 electrons. And in this compartment, the silver ion will actually get reduced. So silver ion, Ag+. Oh, and I forgot to show that's in the aqueous phase. Aqueous silver ion will pick up 1 electron and turn into solid silver. And so there are your two half reactions that correspond to what's going on in each of these half cells. If the notion of a half reaction doesn't sound familiar to you, well, it should, because we covered it way back in video number 4 when we talked about oxidation and reduction. And I'll review a bit of that here, but not too much because we've covered it before. So in order to balance the overall reaction, I would need a 2 here, and a 2 here, and a 2 here, and now the electrons are balanced. So the total moles of electrons exchanged per run of this redox reaction would be 2 electrons. It's always going to be the least common multiple of the number of electrons that shows up in either of the two half reactions. Least common multiple of 1 and 2 is 2. If it was, for example, instead of silver, let's say it was aluminum ion, Al3+, plus 3 electrons, then least common multiple between 3 and 2 would be 6. I'd multiply this whole thing by 2, and I'd multiply the top half reaction by 3 in order to get 6 electrons each, so they cancel out. Anyway, once you've got the moles of electrons matching, you can combine the two half reactions into an overall reaction. So our overall process, I guess I'll write it down here, is solid copper plus 2 silver ion becomes copper ion plus 2 solid silver. Okay, so going back to this voltaic cell, which I haven't finished drawing, by the way, for those of you who've seen voltaic cells before and you're shouting at the screen that I'm missing something, don't worry, I'll get to it. So atoms of copper from this bar of copper will turn into copper ions. They'll turn into new copper ions, and a pair of electrons will be released. A pair of electrons will be generated. Those electrons will start going up through the wire, and then they'll eventually make their way over to this side. Once they make their way to this side, the electrons will attract the silver ions. The silver ions will come closer, they'll pick up the electrons, and they'll deposit as solid silver metal. So silver ions from here will pick up an electron and turn into solid silver metal on top of the surface of this silver metal bar. And so over time, what you'll see is that this bar of copper starts shrinking because, well, it's dissolving. Its mass is going into the solution, whereas this bar of silver starts getting bigger and thicker. It starts gaining mass because silver ions from the solution are depositing on top of it. But this creates a bit of a problem because you're removing positive charge from this solution, leaving behind some nitrate ions, so the overall charge in the solution is now negative. And over here, you're adding copper ions, and the overall charge of the solution is becoming more positive. This is a problem because if the charge of the solution over here gets negative, well, then it's going to start repelling the electrons that are trying to come down into the solution. If this solution gets too negative, it starts repelling the electrons that are trying to come down. And if this solution becomes too positive, then it'll start pulling down the electrons that are generated in your copper metal bar that are trying to climb up. So you need to keep the solutions neutral. You can't let the solutions get charged. You have to keep the charge balanced. And in order to achieve that, what we use is something known as a salt bridge. What we use is something known as a salt bridge. So usually it'll be in the shape of this upside down U. And there will be this semi-permeable gel over here. And inside of this salt bridge, as it's called, you'll have some sort of soluble salt. For example, let's say there's potassium nitrate in here. Potassium nitrate. And what'll happen is if a negative charge starts developing here, potassium ions will get pulled out of the salt bridge and they'll move into the solution. So potassium ions will start migrating here. So that's potassium ions. And over here, if this solution starts getting too positively charged, then nitrate ions will start flowing this way. And that helps keep the charge all balanced. So you can get this process to continue for a while until, of course, you run out of material in your salt bridge, or until this copper bar completely dissolves and is gone. But yeah, during that process you can generate a fair amount of electricity. So in order to calculate how much electricity you're generating, what we use is a set of standard, what we call standard cell potentials. We calculate a standard cell potential. And here's a table that has some of these standard cell potentials. So silver is actually the first one on there. It's got a half cell potential of positive 0.7996 volts. Let me find copper. So first let me write down silver before well, it's going to be the first one, so I'm not going to lose its place. But for silver, I guess I'll write it next to the reaction itself. Here the silver is getting reduced, so E reduction of silver is equal to positive 0.7996 volts. And for copper, if I scroll down, where is copper? Okay, we've got two different copper reductions. Actually, three. I want this one. So 0.34. Copper 2 ion plus 2 electrons gives us solid copper. Okay, so that's positive 0.34, but these are reduction potentials. Do they even mention that here? No, they don't. Okay, that's an oversight on their part. But yeah, these are what are known as reduction potentials, standard reduction potentials. Copper is not getting reduced, it's getting oxidized, so E reduction of copper, that's equal to positive 0.34 volts. But this copper is getting oxidized, so you can actually calculate its oxidation potential, which is the exact negative of its reduction potential. So E oxidation of copper is going to be, I don't even have enough room to fit it in here, do I? Okay, let's write it over here instead. E oxidation of copper is equal to negative 0.34 volts. Okay, and if you wanted to calculate the total cell potential, what we call E cell, or standard cell potential, I should use the degree symbol here because this is going to be done under standard conditions, and those standard conditions are the same as they were for thermodynamics. All pressures are 1 atmosphere, all concentrations are 1 molar, and then temperatures can be whatever. So yeah, these are going to be 1 molar solutions. 1 molar and 1 molar. Anyway, standard cell potential is going to be the reduction potential of whatever gets reduced plus the oxidation potential of whatever gets oxidized. Or, typically what they tell you is you take the reduction potential of what gets reduced minus the reduction potential of what gets oxidized, which is effectively the same thing. So in this case, positive 0.7996 plus negative 0.34, what's that going to give us? 0.7996 plus plus negative 0.34 is going to round to 0.46, positive 0.46 volts. Now, I can hear some of you going, wait, you multiplied the silver's reduction half reaction by 2. Doesn't that mean that you have to multiply the reduction potential of silver by 2? Shouldn't it be 2 times 0.7996 plus negative 0.34? No, it shouldn't be, because volts are joules per coulomb. This isn't something that most chemistry instructors will tell you, but they should. 1 volt is equal to 1 joule per coulomb. 1 volt is equal to 1 joule per coulomb of charge. It's the ratio of energy to charge. So even if I double everything here, yeah, it's going to double the amount of energy in this half reaction, but it's also double the amount of charge. Double the energy over double the charge is the same energy per charge. It's the same joules per coulomb. So multiplying half reactions does not have any effect on the half cell potential. No effect when you multiply, because voltages are ratios, and those ratios stay constant even when you multiply the half reaction. Okay, I just realized I forgot to mention something. So we give two special names to the two different compartments, the two different electrodes that are involved in a voltaic cell. The electrode where the oxidation happens is always called the anode. So oxidation, the electrode where oxidation happens is called the anode. So in this case, that's the copper side. So oxidation happens at the anode. And reduction happens at the cathode. Reduction happens at the cathode. And an easy way to remember which one is which, take notice that the words oxidation and anode both start with a vowel, and take notice that the words reduction and cathode both start with a consonant. So that's an easy way to remember. Oxidation always happens at the anode, reduction always happens at the cathode. It's true for voltaic cells. It's also going to be true for something we see later, which is the electrolytic cell. Okay, and I guess this would be the negative electrode, because this is where the negative charge comes from. So that's like the negative end of your battery, while this is the positive electrode. Let's see, do I have that right? I feel like I've got that wrong. Maybe I'm thinking too much about the physics of it and the definition of current here. Yeah, the anode is the negative electrode and the cathode is the positive. Yeah. Okay. So, in case my drawing isn't all that good, there is a nice diagram for a galvanic cell that you can see that's probably clearer than what I've got. So, there's that. And I guess they used the same example as I did. Anything else that I need to talk about with regard to galvanic cells? Oh, there is one thing. Choosing the right material to put in your salt bridge. So I chose potassium nitrate here. If I had chosen something like, if I had chosen something like potassium chloride, maybe this isn't the best example. But if the roles of the silver and copper were reversed, if it was the silver that was getting oxidized and you were generating silver ions in this compartment, and let's say we had something that was even less reactive than silver over here, and you had something like potassium chloride inside of your salt bridge, and the chloride ions started migrating towards where the silver is, that would pose a problem, because you'd be... Oh, actually, no. Even as is. Yeah, forget about that hypothetical scenario. We don't have to reverse the roles of the copper and silver here. We can just do it with the setup that we currently have. If this was potassium chloride instead of potassium nitrate, then some of the chloride ions in the salt bridge might come into contact with the silver ions and start precipitating out the silver, and that will basically kill your voltaic cell. you'll run out of silver ions, or you'll run out of chloride ions from your salt bridge, whichever happens first. You run out of material and you stop generating electricity, so no good. Be very careful about your choice of salt bridge. It can be almost anything as long as it doesn't have unwanted interactions with the ions in your half cells. Okay, is there anything else I need to comment on regarding standard cell potentials? Well, I guess let's talk about the nature of voltage and where standard cell potentials actually come from. So, the thing with standard cell potentials is that you can't calculate them for an individual metal, for an individual oxidation or reduction. The only way to calculate the voltage is to calculate the voltage difference between 2 points. There is no absolute voltage. We have to define something as our zero reference point and then compare everything against that to determine what the individual voltages should be for, individual metals and their oxidations or reductions. So you can only ever calculate the voltage difference between two electrodes, which is why we have to come up with something, or, well, we don't have to, but it's useful to come up with something that serves as our zero of voltage. And in the case of voltaic cells, the half cell that we designate as zero, the one that we define as having a half cell potential of 0, is what's called the standard hydrogen electrode, or SHE. And here is an illustration of the standard hydrogen electrode, the SHE. So basically they have a piece of platinum metal. Since hydrogen itself is not a metal, you can't just dip it into the solution as a metal bar, so you have to use some other surface, something that allows for the oxidation or reduction of hydrogen without directly interacting with hydrogen. So platinum is a pretty good choice because it allows hydrogen ions to actually dissolve through it. Or, well, I guess hydrogen atoms in general. And yeah, it's a good surface for transferring hydrogen back and forth between the solution phase and the gas phase. But otherwise, platinum is what we would call relatively inert with respect to hydrogen. So we use that as the metal that gathers the electrons that are exchanged with either the hydrogen ions or the hydrogen gas. And yeah, that's your standard hydrogen electrode. It's at your standard pressure of 1 atmosphere for the hydrogen gas and a concentration of 1 molar for the hydrogen ions. And if you connect it with anything else, you can calculate the cell potential. So here's an example of that. If you connect the standard hydrogen electrode on one side to a copper electrode on the other side, you get a voltage difference between them of positive 0.337 or positive 0.34, as we got from our data table earlier. And yeah, the total cell potential being 0.337 tells us that reduction potential of copper minus reduction potential of the SHE is 0.337, and we know that the reduction potential for the SHE is 0 because we defined it as such, and there you go. That's how we define the standard reduction potential of copper to be positive 0.337 or positive 0.34 at 298 kelvins is what the diagram says. And of course at different temperatures you'll probably get different results, but it's pretty typical for galvanic cells to run at room temperature. If you're going to make this setup in a lab, there's no reason to deliberately make the room cold. So yeah, there you go. That's the standard hydrogen electrode. That's how we come up with the numbers that you see in the standard reduction potentials table. Actually, let me scroll through these real quick so that you can refer to them as needed for some of the problems that we'll be doing later. Keep in mind some of these metals are transition metals, and they might have different oxidation states, so make sure to choose the correct one based on that. You also see some nonmetals in there, which shouldn't be a surprise now that you've seen how the standard hydrogen electrode works. I think there's like 4 pages of these. They could have definitely fit 2 columns of these into 1 page. I just feel like they wasted a lot of space here. Well, maybe you don't see the white margins because I've narrowed down the view, but if you download the book, you'll see that practically half of the page is white space. Okay, there we go. That should be all of them. Let's go ahead and switch back to our camera. Actually, wait, do I want to switch back to the camera? Well, yeah, I guess I might as well. So, earlier we calculated that the standard cell potential for a silver and copper 2 ion galvanic cell is going to be 0.46 volts, 0.46 joules per coulomb. In general, if E cell is positive, if E cell is greater than 0, then that's a spontaneous process. If we get a positive value for E cell, it's going to be spontaneous. If we get a negative value for E cell, it's going to be non-spontaneous. In a spontaneous process, the half cell that has the higher reduction potential is going to be the one that gets reduced, and the one with the lower reduction potential is always going to get oxidized. So you'd have the reduction potential of the higher one minus the lower reduction potential, which always gives you a positive E cell. Remember, you can calculate E cell either as, I should probably write it down. You can calculate E cell either as the reduction potential of what gets reduced, in other words, the reduction potential at the cathode, minus the reduction potential of the anode, or alternatively, you can say E cell is equal to the reduction potential at the cathode plus the oxidation potential at the anode. the negative of the reduction potential at the anode is the oxidation potential at the anode. So both of these equations are equivalent to each other. I like to think of it this way, but they'll teach you to memorize this version of the equation because, well, all of the potentials listed in your data tables are reduction potentials. And all the reactions that accompany them are reductions. If you want to write the oxidation reaction, you simply flip the half reaction. But yeah, for a spontaneous process, whichever one has the higher reduction potential will become the cathode. So if you're subtracting reduction potentials, you'll always get the bigger one minus the smaller one gives you the cell potential. And of course, if you forcibly make it go the other way around, if you somehow force the flow of electrons to go up from here and then down this way, then you'll get a negative cell potential. It'll be a non-spontaneous process, so it won't happen automatically, but you know, if you put in the work to make it happen, if you put in energy from some external source, you can definitely do that. I don't know why you would want to, because the whole point is to generate energy, but it's something you can do. Okay, so positive cell potentials are associated with a spontaneous process. In that case, a positive cell potential should correspond to a negative delta G, should correspond to a negative free energy change. And it does. So we have a formula that connects cell potentials to free energy. It's called the Nernst Equation. It's called the Nernst Equation. And it simply says that delta G is equal to negative NFE. Or, alternatively, delta G standard equals negative NFE standard, where E, of course, is E cell. Or it doesn't even have to be a cell. It can just be the overall reaction that happens across both half cells. So if I wanted to just calculate the free energy change for this reaction, if I had this reaction happen in just one flask or one beaker, and I wasn't setting up a voltaic cell, then yeah, E cell is also the change in voltage for the overall reaction. So you don't necessarily have to make a voltaic cell in order to have an E value, which is why we don't call it E cell in this equation. It could just be E reaction. It could just be E could be E cell, or it could just be E of the reaction. Okay, so what is N and what is F in this equation? N is the number of moles of electrons exchanged. I talked about this earlier. In the case of copper and silver, the number of moles of electrons exchanged when you write out the half reactions in order to balance the electrons, that happens when the balancing coefficients are 2's. So it's the least common multiple of the electrons that show up in each of the half reactions. In this case, for copper against silver, N would be 2. If I did copper against aluminum, if I did copper 2 ion versus aluminum, let's do it here as an example. If I had, let's see, aluminum is higher in activity, so aluminum will get oxidized, copper will get reduced. So that's copper 2 plus 2 electrons wait, what am I doing? Yields copper metal, and then aluminum solid becomes aluminum ion plus 3 electrons. Multiply the reduction half reaction by 3. So multiply all that by 3, multiply all that by 2, and that'll result in 6 electrons on the left, canceling with 6 electrons on the right. So for this redox reaction, N equals 6. So N is the number of moles of electrons exchanged per run of the overall balanced reaction. Okay, so that's the N value. What about F? So F is what's known as the Faraday constant. F is the Faraday constant, named after Michael Faraday. And it's basically the number of coulombs of charge in a mole of electrons. It's the total charge, or the magnitude, I should say, of the total charge, the absolute value of 1 mole of electrons. Not quite right because it's actually the absolute value, but you know, I'm not gonna make the definition too wordy. So the charge of an electron, is, or I should say the absolute value of the charge of an electron, the elementary charge, is equal to 1.602 times 10 to the negative 19 coulombs of charge. If I have 1 mole of electrons, then just multiply this by Avogadro's number. So I guess I'll do that in green. If I do 6.022 times 10 to the 23rd times 1.602 times 10 to the negative 19, then that gives us I mean, I already know the outcome, but I want to see how many sig figs we actually get for it. So I'm getting 96,472, probably because I didn't use enough digits of Avogadro's number. But the point is, it's about 96,500. What they'll tell you in textbooks is that it's going to be 96,485 coulombs per mole. Coulombs per mole of electrons exchanged. And usually they'll round it to 96,500. Okay, so let's work out the units here. Delta G standard is going to equal negative, let's see, N is in moles of electrons. The Faraday constant is in coulombs per mole of electrons. And E, the cell potential, is in volts, which is the same as joules per coulomb. Joules per coulomb. So moles and moles cancel out, coulombs and coulombs cancel out, and you get delta G in joules. Be very, very careful about that. In the previous video, we got used to delta G being in kilojoules. If you apply the Nernst equation, and you plug in the cell potential in volts, you will get joules. And if you need to convert that to kilojoules, you need to remember to do so. You need to remember to divide by 1,000. Nernst equation typically gives you delta G in joules. Okay, I think that's everything. So let's do a quick review of, well, we've already reviewed balancing redox equations by balancing their half reactions, but we haven't done a review of balancing redox equations under acidic or basic conditions. And that's something that you'll need to be able to do for this chapter. So let's pull up some problems and see what we've got. First set of problems shouldn't be anything too difficult. It's basically a review of video 4. Identify each half reaction below as either oxidation or reduction. I'm not going to review that with you. We've seen a couple examples already in this video, and there's plenty more in video number 4. If at this point you can't recognize an oxidation from a reduction, then maybe you should stop this video and go back and review video number 4. Number 2, same thing. Number 3. Okay, here we go. Balancing in acidic solution. So let's do one that actually has oxygen in it. You know what? No, I'll skip this and we'll do one that's in basic solution because it has all the same steps as acidic solution anyway, except for the last 1 or 2 steps. Okay, moving on. 5, identify the oxidant and reductant in each reaction of the previous exercise. That's something that was covered in video number 4. The oxidant is the thing that gets reduced. The reductant is the thing that gets oxidized. And how to tell whether or not something got oxidized or reduced, you look at the change in oxidation numbers. And if you've forgotten how to calculate oxidation numbers, well, I think you already know what I'm going to tell you. Go back to video 4. Number 6, balance the equations below assuming they occur in a basic solution. Okay, here we go. So let's do part A. Let's do part A just as a quick review of balancing redox equations in basic or acidic solution. So we've got the sulfite ion plus copper 2 hydroxide yields sulfate ion plus copper 1 hydroxide. I don't know why they put parentheses around hydroxide for copper 1 hydroxide. But there we go. So let's go ahead and try to balance this. First, we have to split it up into 2 half reactions. And remember, this was under basic conditions. So balance the half reactions, or split it up into half reactions and then balance them. So we've got sulfite goes with sulfate. So that's going to be SO3 2 minus and SO4 2 minus. And then copper 2 hydroxide and copper 1 hydroxide. Copper 2 hydroxide turning into copper 1 hydroxide. let's see what we've got. So step 1, balance all the non-oxygens and non-hydrogens. So sulfur and sulfur, those are balanced. Copper and copper, those are balanced. Then balance the oxygens with water. Every water molecule contains 1 oxygen. So we've got 4 oxygens here and 3 here. So I'm going to need to add 2 waters. Or, no, not 2, just 1. Just add 1 H2O. And now we've got 4 oxygens on the left and 4 on the right. For copper 2 hydroxide, that's 2 oxygens. Copper 1 hydroxide just has 1 oxygen. So add 1 water here to get the oxygens balanced. After balancing oxygens, balance hydrogens with hydrogen ion. Even though it's a basic solution, we can pretend it's acidic and then we'll neutralize the hydrogen ions later. So 2 hydrogens here would need 2 hydrogen ions here. And let's see, we've got 2 hydrogens here and 3 hydrogens here. So I would need to add 1 hydrogen ion here. Is that right? 2 plus 1 is 3, and yeah. Okay, that leaves us with having to balance the charges now. So for the first half reaction, total charge on the left is -2, total charge on the right is 0, so I need to add 2 electrons on the right so that I've got -2 on the right and -2 on the left. For the second half reaction, we've got a total charge of +1 on the left and a total charge of 0 on the right. I would need to add 1 electron over here so that the total charge on the left is 0. And in case you've forgotten from video number 4, it doesn't matter that the charges on the left and right of the first half reaction are -2s, while on the left and right of the second half reaction they're 0s. They don't have to match with each other. I don't have to bring the -2 up to a 0 or the 0 down to a -2. I just have to make the left-hand side match the right-hand side in terms of charge for each half reaction, regardless of how much charge it is that ends up on both sides. It doesn't have to match for both half reactions, it just has to match for both sides of each individual half reaction. But the 2 half reactions, they don't have to match each other in terms of how much charge there is. Okay, I'm gonna need to multiply this by 2, and then that'll help me cancel out my electrons, and then, yeah, add those up and get your new overall reaction. So it's going to be sulfite plus 2 copper 2 hydroxide plus 2 hydrogen plus 1 water. Does that cover everything on the reactant side? Yeah, looks like it. We've got all our items. And then on the right-hand side, we've got sulfate ion plus 2 copper 1 hydroxide plus 2 hydrogen ion plus 2 times H2O, that's plus 2 waters. Cancel out anything that shows up on both sides, so I can cancel 1 water each. I can also cancel the 2 hydrogens, but I'm not going to do that because I want to actually show the additional 2 steps for dealing with basic solution. In this case, I guess the fact that these hydrogens cancel shows that it doesn't matter if it happens under acidic or basic conditions, because you're not going to have any leftover hydrogen or hydroxide ions. But yeah, I'm going to keep the hydrogen ions in here just so that we show under basic conditions the next step would be to neutralize your hydrogen ions by adding hydroxides. So I would add 2 hydroxides here and 2 hydroxides here. Add the same number of hydroxides to both sides of the equation, and that will create water. Hydrogen plus hydroxide gives water, so you'd end up with sulfite plus 2 copper 2 hydroxide plus 2 water yields sulfate plus 2 copper 1 hydroxide plus 2 water, and then you'd cancel out any water that shows up on both sides. In this case, you can remove 2 from here and 2 from here, and you're done. So your balanced redox reaction is sulfite plus 2 copper 2 hydroxide gives you sulfate plus 2 copper 1 hydroxide. And there you go. So that's balancing a redox equation under acidic and basic conditions. If it was acidic conditions, you would stop right before we added the hydroxides on both sides. Okay. What else do we have here? Number 7, identify the oxidant and reductant of each reaction of the previous exercise. We already talked about how to do that. Why don't hydroxide ions appear in equations for half reactions occurring in acidic solution? I think that's fairly obvious because there aren't many of them present in an acidic solution to begin with. The only hydroxides that would be present are a few from the autoionization of water, and it's going to be a small amount of hydroxide. The more acidic the solution, the less hydroxide that's in there. Number 9 is basically the same thing. Why aren't there hydrogen ions when the half reactions occur in basic solution? Number 10, why must the charge balance in oxidation and reduction reactions? I mean, it's just conservation of charge, really. And yeah, the electrons have to cancel out. The electrons have to cancel out. Electrons that are removed from one substance have to be gained by another substance. You can't just have, you can't have something like, say, aluminum and let's do, I don't know, zinc. You can't do something like aluminum reacting with zinc ion, where aluminum produces 3 electrons and zinc absorbs 2 of them, and you're left with aluminum 3 ion plus solid zinc plus a leftover electron. That doesn't happen because if you want to eject an electron from an atom and not have that electron picked up by some other atom or ion, then, well, we know a way to do that. You hit the aluminum, in this case, with photons. But that's not what's happening in a chemical reaction. Aluminum and zinc aren't absorbing photons from each other or emitting photons at each other. That's just not how it works. They're physically exchanging electrons, and it has to be a complete exchange. So no free-floating electrons. The charge must balance, the electrons must cancel. Okay, so that takes care of that set. Next up, 11, write cell schematics for the following cell reactions using platinum as an inert electrode as needed. Oh, so I guess they mean, okay, they call them cell schematics here. Interesting. Usually we call this the shorthand notation for the reaction in the galvanic cell. But basically they want you to write things like what you see in problem 12, actually. So here's how that goes. You always write the oxidation first and then the reduction. And for the oxidation you write, basically just write the oxidation half reaction, or the substances in it. Specifically the thing that's being oxidized pre and post oxidation. So if we do part A of number 11, which is magnesium solid and nickel 2 ion becoming magnesium ion and solid nickel. So the magnesium is getting oxidized, so that's magnesium solid turning into magnesium ion. And then this double bar, I believe it's supposed to represent the salt bridge. I mean, okay, I guess, but whatever. The double bar separates the two half reactions from each other as far as I'm concerned. As for it representing the salt bridge, I don't know why anyone would think salt bridge when they see this, but that's a thing that people say. Anyway, the other half reaction is the reduction of nickel. So you've got nickel ion in the aqueous phase turns into nickel metal. And there you go. So I guess this book calls this thing a cell schematic. It's also called the shorthand, I believe it's called shorthand cell notation or half cell notation. But yeah, that's what that is. So it's always the oxidation first and then the reduction. And the way I remember that is because, well, the way I think of it is you have to release electrons first via oxidation so that those electrons can then be picked up, so that something can get reduced by picking up those electrons. You don't pick up electrons first and then produce them. Electrons have to be produced first so that they can be picked up. And technically it all happens in an instant, so there isn't really much time for a first event and a second event. But, if it were to happen in steps, then the oxidation would happen first. But it all is supposed to happen at the same time. Well, I guess when you split up the compartments like this, you make it so that, yeah, the electrons have to be generated first, and then there's a little bit of a time gap during which the electrons have to travel all the way over to here before the reduction can happen. But that's actually why we have to split them into two compartments. We can't just mix your silver nitrate and copper chloride solution into one big vessel. First of all, the chloride would precipitate with the silver, which is no good. But even if this was copper nitrate, mixing them is still not going to help you, because if I were to create just one big container and put my solid copper and my solid silver into a solution that contains copper nitrate and silver nitrate, let's see, that's going to require one more nitrate to balance out the charges. If I had this set up and then I connected these by a wire, if I connected the copper and silver bars by a wire, you wouldn't get any sort of electricity reading here, because the silver ions can just walk up to this copper bar and take the electrons directly. The electrons would have no reason to go the long way around to come to the silver, because the silver ion can just interact directly with this bar of copper. Same thing with the silver interacting with the copper ions. The silver in this metal bar can just wait, is that right? No, the copper ions aren't going to do anything. It's just the silver ions. The silver ions will start basically swapping places with the copper atoms in the bar, and you'll see that this bar of copper turns silver because atoms of silver are depositing on the surface where atoms of copper are ionizing and dissolving out at the same time. So yeah, this isn't going to work. The electrons can just be traded between the silver ion and the copper metal directly without needing to go all the way around in the wire. Anyway, carrying on. So, writing those cell schematics, as this book likes to call them, isn't that hard. Oxidation happens first, reduction happens second, and really all you have to do is write out the thing being oxidized before oxidation and after, and the thing being reduced before reduction and after. Nothing too challenging there. Going the opposite direction, so problem 12, they give you the schematics and they want you to write the reaction. That's not hard to do either. I guess we'll just do the first one as a quick example. So magnesium solid to magnesium ion, they said. So that represents this half reaction. And then they had copper ion to copper solid, copper 2 ion to be specific, so that picks up 2 electrons and becomes solid copper. There we go. Nothing too bad there. 13, write a balanced equation for the cell reaction of each cell in the previous exercise. We know how to do that. Combine. Oh, you don't see it in front of you. Yeah, that's 13. So it's just asking us to write the total, write the overall reaction, which isn't hard to do. You add the two half reactions after making sure that the electrons can cancel out, and we've done it before. It's nothing new. Okay, 14, balance each reaction below and write a cell schematic representing the reaction as it would occur in a galvanic cell. Well, we've already been through stuff like this. Split it up into half reactions and go through all the necessary steps that you would go through when balancing. And of course, use your hydrogen ions and hydroxide ions as needed if it's happening under acidic or basic conditions. 15, identify the oxidant and reductant. We've been over how to do that. What else do we have? From the info provided, use cell notation to describe the following systems. In 1/2 cell, a solution of platinum 2 nitrate forms platinum metal, while in the other half cell, a copper metal goes into copper nitrate solution with all solute concentrations 1 molar. Oh, okay, so they just want you to write the... Yeah, now they're calling it cell notation. So whether you call it a cell schematic or cell notation, you're basically just writing one of these. That's what they're asking for. Okay. What else do they have? 17, why is a salt bridge necessary? We've already explained. 18, an active metal electrode as opposed to an inert metal electrode like the platinum in the standard hydrogen electrode. An active metal electrode was found to gain mass as the oxidation reduction reaction was allowed to proceed. Was the electrode an anode or a cathode? The cathode is where the reduction happens, and the cathode is where metal ions from the solution turn into solid metal that deposit on the surface of your electrode. So, yeah, if it's gaining mass, it was the cathode, not the anode. And 19 is basically the exact opposite question. 20, the masses of 3 electrodes, A, B, and C, each from 3 different galvanic cells, were measured before and after the cells were allowed to pass current for a while. The mass of electrode A increased, that of electrode B was unchanged, and that of electrode C decreased. Identify each electrode as active or inert, and note, if possible, whether it functioned as anode or cathode. Okay, so electrode B, its mass was unchanged, so it must have been inert. Just like the platinum in the standard hydrogen electrode, it neither gains nor loses mass, it just kind of serves as a conduit for the hydrogen ions and hydrogen gas to, change into one another. It's neither consumed nor produced. So that's electrode B. And then electrode A increased in mass, it must be the cathode. Electrode C decreased in mass, it must be the anode. That wasn't too hard. Okay, next we've got calculate the standard cell potentials for each reaction below and note whether the reaction is spontaneous under standard state conditions. You do need to make sure you split it into half reactions, or at the very least know how many electrons are being gained or lost by each species. Remember, some transition metals will have multiple oxidation states, so you have to choose the cell potential that corresponds with whatever change in oxidation state you have for the transition metal. It's not always fixed. For example, copper ion, you could have it partially reduced if it's the copper 2 ion. You could have it partially reduced from copper 2 to copper 1, or you could have it completely reduced from copper 2 to solid copper. So you have to look up the correct half cell potential based on what the change in the oxidation state really is. So aside from that, it should be pretty easy. Reduction potential of whatever got reduced minus reduction potential of whatever got oxidized, or reduction potential of what gets reduced plus oxidation potential of what gets oxidized. Not too hard to figure out. 22 is more of the same. Okay, let's do one of them. So let's do 22A. Let's do 22A. So we've got manganese and nickel. Manganese and nickel 2. Turning into manganese 2 and solid nickel. Okay, manganese loses 2 electrons, nickel gains 2 electrons, so the half reactions are manganese turning into manganese 2, producing 2 electrons, and nickel 2 gaining 2 electrons, producing nickel metal. And now we just look those up in our, in our data table. Let's go ahead and see where those are. So manganese and nickel. Okay, I see nickel. Negative 0.257 for its reduction, which is what we have. So that's negative 0.257 when it's getting reduced. Manganese, on the other hand, is getting oxidized, so there's manganese. So negative 1.185 when it's reduced. When it's oxidized, that's positive 1.185. So positive 1.185. And those are in units of volts, of course. Let's switch back to our full camera view. Okay, so positive 1.185 for the oxidation, minus 0.257 for the reduction. Overall, the E cell or E reaction, whatever you want to call it, is going to be equal to 1.185 minus 0.257 is 0.928 volts. 0.928 volts. Okay, was there anything else on this page that we needed to go over? 23, write the balanced cell reaction for the cell schematic below, calculate the standard cell potential, and note whether the reaction is spontaneous under standard state conditions. Oh, and by the way, for the one we just did, E came out positive. That corresponds to a spontaneous reaction. And I think I forgot to mention this when bringing up the Nernst equation, actually. Let me switch back for a second here. When we talked about the Nernst equation, I think I forgot to point out the reason for the negative sign is because a positive cell potential is spontaneous, which means a positive E needs to go with a negative G, so that's why the negative sign is there, just to ensure that positive E values go with negative delta G values. That was probably apparent to most of you, but you know, sometimes it's helpful to have those things pointed out. Anyway, back to our problems. Next sheet. Determine the cell reaction and standard cell potential at 25 degrees Celsius for a cell made from a cathode half cell consisting of a silver electrode and 1 molar silver nitrate, and an anode half cell consisting of a zinc electrode in 1 molar zinc nitrate. Is the reaction spontaneous at standard conditions? So basically the same as what we just did, except they didn't write the equations for us. I mean, in this case, they don't have to, because silver and zinc, there's only one possible oxidation state for, well, two possible oxidation states. 0 and positive 1 for silver, and 0 and positive 2 for zinc. But yeah, outside of that, it's basically the same as the problem we just did. 25, determine the cell reaction and standard cell potential. Looks like it's the same as 24. 26, write the balanced cell reaction for the cell schematic below, calculate the standard cell potential, and note whether the reaction is spontaneous under standard state conditions. So we've seen something like this as well. The platinum is mentioned there because, well, you're dealing with the standard hydrogen electrode, so the platinum needs to be there, but it's kind of like a catalyst. The same amount of it is present at the end as there was at the beginning, so it's unchanged, but you can mention it in your shorthand cell notation. Okay, nothing new there. (27) For each pair of standard cell potential and electron stoichiometry values below, calculate a corresponding standard free energy change in kilojoules. And they've given us the N value. So this is just plugging into the Nernst equation. They've dumbed it down considerably. Okay, let's just do it. So we've got part A, 0 volts, and n equals 2. That's just going to give you delta G standard equals negative, let's see, it's going to be negative 2 times the Faraday constant, what was it, 96,485. Times E cell, which is 0. So that's just a 0. For the next one, we've got positive 0.434 for our cell potential. So we actually have something here. N equals 2, so that's negative 2 times 96,485 times positive 0.434 volts. That is going to give us, let's see, the negative 2, that's an exact number, so I don't have to worry about it in terms of sig figs. 96,485 is 5 sig figs times 0.434 is 3 sig figs. So rounding to 3 sig figs, that's negative 83,700. And that's in joules. In kilojoules, that's negative 83.7 kilojoules, or kilojoules per mole, if you prefer. Okay, and part C is virtually the same, so I think we're done there. 28 is the reverse. They give you the free energy and they want you to calculate the cell potential. Do I really need to go through it? Okay, we'll just do one of them. 12 kilojoules per mole with N equals 3. 12 kilojoules per mole with N equals 3. Let's do it up here. I guess I haven't done red on this page yet. So 12 kilojoules is 12,000 joules, so 12,000 equals negative NFE. They gave us N equals 3 for this one, times Faraday's constant, 96,485, times E, which we need to solve for. So 12,000 divided by negative 3 is negative 4,000. Divide that by 96,485 and round to, it's supposed to be 2 sig figs, so that gives us E equals negative 0.041 volts. And there we have it. Okay, and that was a standard cell potential. What about non-standard cell potentials? What about non-standard cell potentials? So we can take advantage of what we learned in the previous video. A non-standard cell potential would have a non-standard delta G that goes with it. We said that delta G in general is equal to delta G standard plus RT ln of Q. And even though we've been drawing single arrows for all of our redox equations so far, we can just easily replace them with double arrows and define a Q value for them. Product over reactant concentration ratios. So the Nernst equation gives us that delta G is negative NFE, so negative NFE non-standard equals negative NFE standard plus RT ln of Q. If I want to find an equation for E non-standard, then just divide everything by negative NF. So we get E non-standard equals, divide by negative NF, that's gone, leaving E standard, and then RT ln Q divided by negative NF, so that's minus RT over NF ln of Q. RT over NF ln of Q. Now, oftentimes, you'll see a simplification of this in textbooks. So R will be plugged in, T will be plugged in as 298 kelvins, room temperature, and the Faraday constant will be plugged in. So you'll get, let's see, E equals E standard minus, since cell potentials are in joules per coulomb, the ideal gas constant is going to be in joules per mole Kelvin, which is 8.314. So that's 8.314 times the temperature, 298 kelvins typically, over N, and then the Faraday constant, 96,485. Times ln of Q. I would just memorize it in this form. I mean, plugging in R and T and F isn't that hard, but you know, just in case you don't see this exact formula in your book, in case you see one of these shortcut formulas, it's good to know where that's coming from. So 8.314 times 298, that's going to be 2480 roughly, and then divided by 96,485. Let's see, 2480 divided by 96,485. I'm getting 0.0257 if I round to 3 sig figs. 0.0257. So E non-standard equals E standard minus 0.0257 over N times natural log of Q. This is still not the end of the simplification that you'll see in a textbook. They'll actually simplify this some more by converting the natural log to a regular log base 10. So apparently, natural log of Q is equal to about I think it was 2.302 or 2.303 times log of Q. And where does that come from? In textbooks, they typically just give you this as a fact without really explaining it, but chemists are not mathematicians after all, and I am a mathematician, so I'll explain where this relationship comes from. So suppose that you wanted to find the relationship between, let's see, that would be ln of x over log of x. And let's say we define ln of x as being equal to y and log of x as being equal to z. So log of x equals z, ln of x equals y. Then you can say an equivalent expression you can say that e to the y is equal to x, and you can say 10 to the z is equal to x. Therefore, e to the y is equal to 10 to the z. Therefore, e to the y equals x equals 10 to the z. Okay, and from here, you can take the log on both sides. You can take, or should it be the natural log? Well, let's try both. If I take the natural log on both sides, natural log of e to the y equals natural log of 10 to the z. Natural log of e to the y just gives you y equals natural log of 10 to the z is z times the natural log of 10. Okay, here we go. And what's the natural log of 10? If you plug it into your calculator, natural log of 10 is 2.303. So y equals z times 2.303. Y is ln of x, so ln of x equals z, which was log of x, times 2.303. And there you go. So that's where that's coming from. Anyway, if you replace the natural log with just an ordinary log base 10, then you can do that at the exchange of multiplying by 2.303. So if you do that, negative 0.0257 ln of q is negative 0.0257 times 2.303 log of q, which is 0.0257 times 2.303 is 0.0592. 0.0592 log of q. So these two are really just shortcut formulas for the specific case where you do things at room temperature, but honestly I would just prefer you do this one. And I hinted at it in the previous video. I said we were going to find a third equation that resembles the Henderson-Hasselbalch equation, and well, now you have it. Right, in the previous video we said that delta G equals delta G standard plus RT ln of Q is similar to the Henderson-Hasselbalch equation in that the value that you're trying to get on the left-hand side equals some sort of benchmark value modified by a logarithmic term. And we showed that something similar is going on with delta G. So delta G is some sort of starting value modified by a logarithm involving concentration ratios or pressure ratios. And same thing for cell potentials. So a cell potential is equal to some standard, some starting value modified by the logarithm of some ratio. Okay, so non-standard cell potentials give you some flexibility if you just mess around with the ratio of products to reactants, if you mess around with Q, you can adjust your cell potential in case you don't like your standard cell potential. This actually allows you to create cells that work even if the standard cell potential is 0. Even if the standard cell potential is 0. So let's say, for example, and here's an easy way to make sure the standard cell potential is 0. Make sure that both of your half reactions are exact opposites of each other. Make sure you're using the same material for both electrodes. So, for example, silver and silver. So let's say I've got a bar of silver here and a bar of silver here. So that's silver and that's silver. And of course we've got our salt bridge. And yeah, the standard cell potential is just going to be 0. If one of these gets reduced and the other gets oxidized, they're going to be equal and opposite half cell potentials that'll just cancel out. So for this, E standard for your cell is going to be 0, exactly 0 volts. How can I still make this work? Simple. By making sure the concentrations of, let's make it silver nitrate, by making sure that the concentrations in the two chambers are different from each other. By making sure the concentrations in the two chambers are different from one another. So let's say this is at a concentration of 4 molar, for example. Let's say it's 4.00 molar. And let's say this is at a concentration of 2.00 molar. Let's say you've got different concentrations like that. Then, let's see, what would happen is silver ion from here would start getting reduced and turning into silver metal, lowering its concentration. Over here, the silver metal will start dissolving, increasing the silver ion concentration, and it'll stop when they both reach a concentration of 3 molar. So this would be the cathode, because this is where reduction is happening. And this would be the anode. And electricity would be flowing this way. Well, the electrons would be flowing this way, but in physics terms, we would say that the conventional current is going the opposite way, because in physics, conventional current is the direction of positive charge movement, which is the opposite of the direction of negative charge movement. Obviously, positive charge doesn't move because it's trapped in the nucleus. But physicists didn't know that at first when they were studying how electricity travels through a circuit. So, they made the mistake of assuming that positive charge moves, and by the time it was discovered that it was actually the negative charges that moved, it was kind of too late to rewrite all the textbooks and whatnot. So we're stuck with it. We'll talk about electric current later when we discuss electrolysis. That's coming. Where was I going with this? So we've got at the cathode, we've got a reduction going on. We've got silver ion. This is from the high concentration compartment, is being reduced into solid silver, and solid silver from the low concentration compartment is being oxidized, so that's Ag plus low concentration plus an electron. So yeah, your overall reaction, I guess the solid silver cancels out, the electrons cancel out, and your overall reaction is high concentration silver being consumed and low concentration silver being produced. Ions in the low concentration chamber are being produced, and that concentration is going up, this concentration is going down. And we can then define Q, the reaction quotient for this, to be the concentration of low silver to high silver. So it'll be Ag plus low over Ag plus high, and high, and then close the brackets. And so we can calculate the non-standard cell potential here. It'll be E equals, let's say that this does occur at room temperature and just use the shortcut formula, one of them. Let's use the bottom one. N equals 1. There was one electron that we canceled out when adding the half reactions. So E is going to equal E standard, which is 0, minus, let's go with 0.0592 over 1 times log base 10 of Q times log of, I guess I'll call it low over high. Log of low over high silver concentrations. So let's see, the low concentration starts at 2 and the high concentration starts at 4, so that's log of 2 over 4, or log of 1/2, negative 0.0592 over 1 times log of, I guess that would be 0.500. Oh, let me do the log first. So log of 0.500, that's 3 sig figs, so 3 decimal places. That's negative 0.301. Negative 0.301 times negative 0.0592 over 1 is positive 0.0178. Positive 0.0178 volts, or joules per coulomb. A positive value, which indicates that, yeah, the spontaneous process is for the high concentration to drop and the low concentration to rise. And this will keep on occurring, of course, until the concentrations become equal, at which point the low to high concentration ratio becomes, well, 1 to 1, and the log of 1 is 0, so eventually you will run out of, well, I wouldn't say you run out of material, but the ratios just balance out and electricity stops flowing. The voltage starts at a high of 0.0178, which isn't really that high to begin with, and just diminishes gradually as these concentrations change until it eventually goes to 0. So yeah, that's the concentration cell. The only driving force behind it is not a difference in potential between the electrodes. It's just a difference in concentration. So that's why this is called a concentration cell. Concentration cell. Even if it's not a concentration cell, even if it doesn't purely rely on differences in concentration to produce a cell potential, even if these are different metals or different materials, I should say, because they don't necessarily have to be metals. Even if these are different, you can still use concentration to your advantage to modify the cell potential. And because there's a dependency on Q for non-standard cell potentials, you can increase or decrease the total cell potential, and therefore you can increase or decrease the spontaneity of the process by altering the concentrations. It's basically Le Chatelier's principle at play. So if I went back to one of my previous examples, let's say, actually let's go to our very first one. Yeah, if we went to this one, so it was copper plus silver ion, and then on the right hand side it's copper ion plus solid silver. The solids don't count, of course, so Q would be copper concentration over silver concentration squared. If I increase the copper ion concentration, if I pour more copper 2 chloride into this chamber, then let's see, what would that do? Would that increase or decrease the cell potential? Well, that would increase the value of Q. That would increase the value of Q, and an increase in the value of Q is an increase in the natural log of Q. So it's an increase in this overall negative term. So you're subtracting more when Q gets higher, and the more you subtract, the less positive and the more negative the cell potential gets. Negative cell potentials are for non-spontaneous processes. So you're actually you're lowering the cell potential and making it less spontaneous in that case. Versus if I were to, let's go back to it again, versus if I were to increase the molarity of the silver nitrate in this chamber, that would increase the product concentrations, which would lower the Q value. Wait, did I say product? That would increase the reactant concentrations, which would lower the Q value, and a lower Q value would result in less being subtracted from E standard, which would lead to a higher overall E value. So yeah, that would make the reaction more spontaneous. But even without going through all that math, if this forward reaction is the spontaneous process, which it is because it results in a positive cell potential, then you already know increasing the reactants drives the reaction forward more, and since the forward reaction is spontaneous, driving it forward more just makes it more spontaneous, increases E cell, makes delta G more negative. So yeah, you can totally explain this in terms of Le Chatelier. You can totally interpret that in terms of Le Chatelier's principle. Okay, I think that takes care of non-standard cell potentials. Let's see if there's a few problems involving that might be worth looking at. So 29, determine the standard cell potential and the cell potential under the stated conditions for the electrochemical reactions described here. State whether each is spontaneous or non-spontaneous under each set of conditions at 298.15 kelvins. Okay, so at that temperature you can use one of the shortcut formulas. And they've given us the concentrations of everything. So, I'm not sure what the half reactions are here. So we've got I can see what it is for silver, but for sulfide, well, no, sulfide isn't getting oxidized or reduced. It's the mercury. Yeah, it's the mercury turning into, I guess that would be mercury 2 ion. Okay, so we would calculate the standard cell potential from there. So you can just look up that information in a data table. And then for the Q value, there's nothing that counts on the product side. They're all solids. So it would just be Q equals 1 over sulfide concentration times silver concentration squared. Okay, at least I'll give you the setup for it. So it would be E equals E standard, which you can calculate from data tables, minus 0.0592 over, what is N going to be? It's going to be 2. Yeah, because the mercury oxidation state increases by 2 and each silver decreases by 1. So between 1 and 2, least common multiple is 2. Log of Q. Nothing on the product side, so we'll just put a 1 in there. And on the reactant side, it's... Oh, actually, the sulfide does the the sulfide concentration should count. So it's over sulfide to the first power. So 0.10 molar is what they gave us. And silver to the second power, they gave us 0.25 molar for silver, so that's 0.25 squared. And yeah, look up the reduction of silver and the oxidation of mercury, specifically the oxidation of mercury from 0 to mercury 2, not mercury 1. And once you've got those, calculate E cell and you're good to go. Plug in the numbers. Part B, the cell made from an anode half cell consisting of an aluminum electrode and 0.015 molar aluminum nitrate, and you can't see that. There you go. Part B, the cell made from an anode half cell consisting of an aluminum electrode in 0.015 molar aluminum nitrate solution and a cathode half cell consisting of a nickel electrode in 0.25 molar nickel 2 nitrate solution. Okay, so again, more of the same. You look up the reduction potentials of the aluminum and nickel 2 ions. It looks like nickel 2 gets reduced all the way to solid nickel, while aluminum metal gets oxidized to aluminum ion. Calculate the cell potential from there by subtracting the reduction potentials. And yeah, plug in your concentrations and determine Q. How many moles of electrons would be exchanged here? N would be 6, because aluminum would lose 3 electrons and nickel would gain 2. Least common multiple between 2 and 3 is 6. I guess I'll set it up. So you would calculate E standard from the data tables, and then it's 0.05. Oh, right, it's still under the same temperature. It's still at room temperature. So 0.0592 over 6 times log of, what would the overall reaction be? You can ignore the solids because they don't contribute to the reaction quotient. So we've got solid aluminum in the reactant side, nickel 2 ion in the reactant side, so it would be the nickel 2 ion concentration, and the aluminum ion concentration from the product side. And I guess you would have to raise them to the appropriate powers. So the aluminum would be multiplied by 2 and the nickel by 3 before balancing. So this will be squared and that will be cubed. And for aluminum, they said 0.015 molar. For nickel, it's 0.25. Okay, and from those two examples, I believe you now know enough to handle the rest on your own. 30, determine delta G and delta G standard for each of the reactions in the previous problem. So once you've got your E values, just multiply them by negative NF. Nothing too hard there. 31, use the data in the appendix to calculate equilibrium constants for the following reactions. Assume it's room temperature unless temperature data is given. Okay, let's do one that's not at room temperature. So let's do part B. Solid cadmium sulfide dissociating into cadmium ion and sulfide ion. Okay, solid cadmium sulfide. Solid cadmium sulfide dissociating into cadmium ion and sulfide ion, and they said it was at a temperature of 377 kelvins. So cadmium going from 0 to +2 and sulfur going from 0 to -2. Let's look those up. I think the S's would be down here, so do we have sulfur anywhere in there? Yes, we do. Okay, there it is. So the reduction of sulfur to sulfide, which is exactly what we have, is -0.47627, We probably aren't going to keep all those decimals anyway, but for now, reduction, so E red of sulfur is equal to negative 0.46, or no, 0.47. Great, messed it up already. E reduction of sulfur is negative 0.47627 volts. And then E oxidation of cadmium is what I'm going to list. Let's go ahead and find it. Okay, found cadmium. So oxidation of cadmium would be the reverse of the reduction of cadmium, so positive 0.4030. I would flip the sign, so positive 0.4030 volts. I also see they've listed cadmium sulfide being reduced into, oh wait, no, that can't be right. That's not for us. Okay. Let's go ahead and get back to our paper here. So now we have everything we need for calculating the standard cell potential. And the standard cell potential in this case is going to be negative, it looks like, which is no surprise to me at all. The forward reaction doesn't look like it would be very spontaneous. This is the dissolution of a highly insoluble solid. Okay, so E is equal to E standard, which is 0.4030 plus negative 0.47627. And that's going to round to 4 decimal places. So that's negative 0.0733. Negative 0.0733 minus RT over NF. So that's 8.314 times 377 kelvins over how many moles of electrons are exchanged. Cadmium loses 2, sulfur gains 2, so least common multiple of 2 and 2 is 2, and then the Faraday constant, 96,485, or 96,500 if you prefer, times, this version was still the natural log version, so times the natural log of Q, and Q is just going to be the product of those concentrations. Cadmium to the first power and sulfide also to the first power. What were the concentrations given as? Let me see. So Oh. Okay. I was Okay, they just want the equilibrium constants, which are calculated from standard delta G values. Okay, we don't actually need this part after all. Never mind, we don't need this part at all. Okay, so E is just equal to E standard, and then delta G standard, they want the standard, or well, they don't want the standard free energy, they want the equilibrium constant, which is calculated from the standard delta G. So delta G standard equals negative NFE standard. Okay, here we go. I was having a brain malfunction earlier. Equals negative, N is still 2 as we explained earlier, and then 96,485 and negative 0.0733. Negatives cancel, so 96,485 times 0.0733 rounded to 3 sig figs is 7,070. 7,070, and then 7,070 times 2 is 14,140, which I guess in 3 sig figs is 14,100. That's 14,100 joules, which equals 14.1 in kilojoules. And now that we've got delta G standard, we can calculate K, because K is equal to E to the negative delta G standard 14.1 over RT. Since 14.1 is in kilojoules, that's going to be 8.314 times 10 to the negative 3 kilojoules per mole Kelvin, and then that times a temperature of 377 kelvins. Okay. And the rest is just plugging in the numbers. You can do that on your own. And yeah, that's 31. So the other parts play out pretty similarly. Let me see what else we've got. (32) Consider a battery made from one half cell that consists of a copper electrode in 1 molar copper 2 sulfate solution and another half cell that consists of a lead electrode in 1 molar lead 2 nitrate solution. What is the standard cell potential? We know how to calculate that by now. What are the reactions at the anode, cathode, and the overall reaction? Easily done. We've seen that before. Part C, most devices designed to use dry cell batteries can operate between 1 and 1.5 volts. Could this cell be used to make a battery that could replace a dry cell battery? Why or why not? So, depending on your answer to part A, if the standard cell potential is between 1 and 1.5, then you can use it. If the standard cell potential is not between 1 and 1.5, you could still use it as long as you play around with the ratios of the concentrations of the copper sulfate and lead nitrate solutions. So it's still possible as long as you mess with the concentrations. I don't know if this problem would allow you to change those concentrations, but you know, in real life you could still use it. Part D, suppose sulfuric acid is added to the half cell with the lead electrode and some lead 2 sulfate solid forms. Would the cell potential increase, decrease, or remain the same? Okay, so you're reducing the concentration of the lead ion. So based on your overall reaction, if the lead is on the... They didn't tell us which one's the cathode and which one's the anode, but if the lead is on the reactant side, then decreasing reactant would shift equilibrium to the left. If the lead is on the product side, decreasing the concentration of product would shift your reaction to the right. And assuming your forward reaction is the spontaneous reaction, assuming the forward direction is the spontaneous direction, if the lead is on the product side, then precipitating out some of it will actually help increase the cell potential and lower delta G, make it even more negative, making the process more spontaneous. But yeah, you can work it out and see what happens, but I've basically described what to expect. 33, consider a battery with the overall reaction. Okay, so basically it was our first example, copper and silver. What's the reaction at the anode and cathode? We already listed them. It was our first example. A battery is dead when its cell potential is 0. What is the value of Q when this battery is dead? Interesting. We would just use the nonstandard cell potential equation. So we would say E nonstandard equals E standard minus RT over NF times ln of Q. And when the battery is dead, E is 0. E standard, what did we get? I think it was like 0.4 something. 0.46. Yeah, we got E standard is 0.46. Okay. So 0.46 minus, I guess if we assume it's at room temperature, we can take a shortcut and do 0.0592 over N would be 2, and then it would be log of Q. Add over to the left-hand side. So we've got 0.0592 over 2 log of Q equals 0.46. Multiply by 2, that's going to be what is that? That's going to be 0.92. And then 0.92 over 0.0592. Rounded to 2 sig figs is 16. So log of Q equals 16, which means that Q would be 10 to the 16th power. Or, well, let's see, so 2 sig figs, 2 decimal places, so it would be 1.00 times 10 to the 16th power. Okay, yeah, that's quite the ratio. Okay, moving on, part C. If a particular dead battery was found to have copper ion concentration 0.11 molar, what was the concentration of the silver ion? Okay, so Q is going to be copper over silver squared, since the copper ion is on the product side and the silver ion is on the reactant side. And the balancing coefficient for silver is 2, so you have to square it. So, yeah, you're basically being told that Q, which is copper ion concentration over silver ion concentration squared, is 1.00 times 10 to the 16 when the battery is dead, and the copper ion concentration is 0.11, so 0.11 over, let's just call it x squared, equals 1.00 times 10 to the 16, multiply x squared, divide 1.00 times 10 to the 16, 0.11 divided by, divided by, what am I doing? 0.11 divided by 1.00 times 10 to the 16 is 1.1 times 10 to the negative 17, and then take the square root of that, and we get x equals, let me put that in scientific notation, 3.3 times 10 to the negative 9. 3.3 times 10 to the negative 9 molar. Okay, and there we go. Why do batteries go dead but fuel cells do not? So you can look up what fuel cells are in your textbook or online. But the way fuel cells work, they can continue working as long as the fuel is being pumped into them, so they don't have to go dead. Batteries have all the material, all their fuel, so to speak, already pre-contained, and once it runs out, it runs out. There's no place to fill it up. You can recharge it. You can try to reverse the process for some batteries. Not all batteries are rechargeable, as you know. But yeah, you can read the FYI sections of the typical chemistry textbook regarding all the different types of batteries and fuel cells and whatnot. 35, use the Nernst equation to explain the drop in voltage observed for some batteries as they discharge. Oh, that's easy. That's because of the Q value changing. That's because of the Q value changing. As the reaction proceeds, the number of products will start to increase and the number of reactants will start to decrease, so the Q value starts growing larger and larger and larger. Therefore, the log, or natural log of Q, starts getting bigger and bigger and bigger. And if you look at the equation for nonstandard cell potentials, as Q gets larger and the natural log of Q starts getting larger, all of these are going to be positive values multiplied by a growing value. So you're subtracting something that's getting bigger and bigger and bigger over time. So if you started with some positive cell potential, eventually this negative term would get large enough to completely cancel it out, and then you'd be at a potential of 0, your battery would be dead. Pretty simple, straightforward. Well, maybe not so straightforward. I mean, you do have to take a few leaps in logic. You kind of have to be on top of your equilibrium game to see it immediately. 36. Using the information thus far in this chapter, explain why battery-powered electronics perform poorly in low temperatures. Why they perform poorly in low temperatures. Well, let's see. Lowering the temperature would lower this value. If this value is, if Q is small enough that the natural log of it is negative, that is if Q is less than 1, then yeah, a decrease in temperature would, if Q is low enough that the natural log is negative, then this whole term, essentially subtracting a negative is the same as adding, so it would be adding to the cell potential if Q is really low. And if it's adding to the cell potential, then you don't want the temperature to be very low, because if the temperature is really low for something that's being added to the cell potential, then you're not adding as much to the cell potential, which means you're not increasing the spontaneity of the reaction that powers the battery as much. But over time, low temperature wouldn't be a bad deal. Once Q gets high enough, it's actually better if the temperature is lower. So this is a kind of it depends sort of question. Okay, so that takes care of that. Next up we have, these are a bunch of questions about corrosion, which isn't really the most important topic. I don't think they focus on it all that much in AP Chemistry or in the college general chemistry course. Maybe they focus on it in IB Chemistry. I don't really know. I don't know IB Chemistry all that intimately, so I can't say for sure, but given that IB Chemistry tends to focus on these side topics a bit, I wouldn't be surprised if corrosion was included. So yeah, you can just read up on it. It's more something that you just want to understand conceptually if you need to know about it at all. But basically, the higher the reduction potentials of metals, the more likely they are to react with oxygen, and oxygen tends to eat away at metals. For example, the rusting of iron. Iron rusts whenever it's exposed to oxygen. Of course, humidity also helps it rust faster. So, that's no good. But then again, you have other metals that, yeah, they'll react with oxygen at first, but then they'll form like this oxide layer that protects it from any further corrosion. An example of that would be aluminum. So when aluminum is oxidized, an aluminum oxide layer forms on the top, which protects all the rest of the aluminum metal that's underneath it. But other than that, what you could do to protect something like iron from corrosion is you could provide what they call a sacrificial anode, something that's even more reactive that can, bear the brunt of the exposure to the oxygen. Something that's more reactive with oxygen, that consumes the oxygen and prevents that oxygen from reacting with the other metal that you're trying to protect. But yeah, that's the corrosion topic. You can read about it. It's not that hard. Even someone who doesn't know chemistry can probably read the section in the textbook that talks about it and come out of it with a good general understanding. So I'm not going to go over this. Instead, I want to move on to the final topic for this chapter, electrolysis. So let's see here. Here we go. So imagine you have the following setup. So you've got, instead of using two electrodes with two different metals dipped in solutions of those metal ions to generate electricity, instead you supply electricity and feed it into the solution. Instead, you run electricity from an external source through the solution. What will happen? Well, you can use this process known as electrolysis to separate the components of a compound. Of course, it would typically have to be an ionic compound. But you can also do electrolysis on water. You can run electricity through water and separate it into hydrogen and oxygen gases. But typically electrolysis is done on salts, and the salts have to either be dissolved or they have to be in molten form. You have to melt them or dissolve them. If they're not soluble, you'll have to melt them so that they're in a form that's able to move around. So how does this work? You plug in a voltage source, a battery basically, and you create an anode which is connected to the positive side of your voltage source this time, and a cathode which is connected to the negative end of your voltage source. Remember, with a galvanic cell, the anode was the negative side while the cathode was the positive side. Here it's the reverse. What isn't reversed is the fact that the electrons still go up the anode and down the cathode. Also, oxidation still happens at the anode and reduction still happens at the cathode. So those things have not changed. Those things have not changed. So in this example, it looks like we're separating sodium and chloride ions to get pure sodium metal and pure chlorine gas. So you've got the chlorine gas, or the chloride ions, I should say, are attracted to the positive anode. They give electrons to the anode and, well, they get oxidized. They go from an oxidation state of -1 to 0, forming chlorine gas. Opposite is happening with sodium. If you look on the right-hand side, you have your sodium attracted to the cathode. It picks up electrons from the cathode and just deposits as pure sodium metal. So that's the basic idea behind it, nothing too complicated. Now, calculation-wise, you can kind of keep track of, well, not kind of, you can definitely keep track of the progress of electrolysis and how quickly you can electrolyze a salt. As long as you know a couple of things. You would need to know, first off, you would need to know the electric current. The electric current, which is sometimes also called the amperage. Electric current or amperage. So electric current you can learn about more in a physics class, but it's measured in units of amperes. Usually it's given the symbol I. So electric current represented with the symbol I, typically in units of amperes. And an ampere, 1 ampere, is equal to 1 coulomb of charge per second. 1 coulomb of charge per second. So if you know how much time has passed while running a given current, you can figure out how many coulombs of charge have been run through your electrolytic cell. So you can say that total charge, and I guess we would use, in physics we use Q for charge, but we already use Q for the reaction quotient, and we use lowercase q for heat, so maybe we shouldn't use Q here. What should we use instead? Let's come up with some symbol. What can I use to represent charge? Okay, I'll just write out the word charge. So charge delivered is equal to your electric current times your time in seconds. If your time is given in hours or minutes, of course you need to convert. Okay, so if we can get our charge in coulombs by multiplying the current with the time, then the only thing left is to figure out how much charge it takes to electrolyze whatever ions you're trying to electrolyze. If you're concerned with, for example, only how much sodium metal you're collecting, and you're not concerned with the chlorine gas generated here, if you're just trying to get some solid sodium for some experiment that you want to do, then you would calculate how many moles of electrons does it take for every mole of sodium that you want to produce. And of course you can just look at the half reaction and go, well, sodium, for every 1 mole of sodium ions you need 1 mole of electrons to produce a mole of sodium metal. So once you've got your moles of electrons, you can multiply by the coulombs per mole, which is just the Faraday constant. And yeah, from there you can calculate how many moles of sodium you're generating. This is probably not making too much sense the way I'm explaining it. It'll probably be quicker to just look at an example. So let's go ahead and actually pull up an example. We've got, what does problem 43 say? If a 2.5 ampere current flows through a circuit for 35 minutes, how many coulombs of charge moved through the circuit? Okay, that's not a full-on problem. That's just calculating charge. So we'll pass 44 for the scenario in the previous question. How many electrons moved through the circuit? Again, that's part of a bigger question. We'll pass. Write the half reactions and cell reaction occurring during electrolysis of each molten salt below. Calcium ion turns into calcium solid. Chloride ion turns into chlorine gas. Combine the half reactions into an overall reaction. Nothing too hard, not too different from what we did with electrolytic cells. Or not electrolytic, electrochemical, voltaic, galvanic cells. Okay, so skip 45. 46, is this a good one? What mass of each product is produced in each of the electrolytic cells of the previous problem if a total charge of 3.33 times 10 to the 5 coulombs passes through each cell? Okay, now we're talking. So let's do part B, lithium hydride. And let's just calculate the mass of lithium that's produced. Yeah, let's just oh, wait. Would that work? Yeah. Let's just calculate the mass of lithium that's produced. So, of course, whatever moles of lithium are produced would equal the moles of hydrogen produced as well, because it's a 1-to-1 lithium hydride ratio. But let's just focus on the lithium. So how many grams of lithium are produced if a total charge, I guess they didn't give us the amperage here, but that's okay. So if we've got 3.3 times 10 to the 5 coulombs of charge that were run through this electrolytic cell, then I know that every 96,485 coulombs of charge is 1 mole of electrons. And for, you know what? I don't want to do lithium after all. Let's do the aluminum chloride, and I'll focus on the aluminum. So for every 1 mole of aluminum, for every 1 mole of aluminum metal collected, that requires 3 moles of electrons. You need 3 moles of electrons to reduce 1 mole of aluminum ion to 1 mole of aluminum metal. You can tell just by looking at the corresponding half reaction. And now that you've got moles of aluminum, multiply by the molar mass and you're done. So what's the molar mass of aluminum? Let me get my periodic table here. Aluminum is 26.98. So 26.98 grams for every 1 mole of aluminum. All right. And of course you could do a similar calculation for the chloride ion that's converted to chlorine gas and calculate the moles and grams of chlorine gas produced. It would still be 3.33 times 10 to the 5 coulombs. It's not like you use them all up on the aluminum and there's nothing left for the chloride. The fact of the matter is, whatever electrons you give to aluminum equals the electrons that you take from the chloride. So the 3.33 times 10 to the 5 applies to both the aluminum and the chloride separately. But yeah, that's how you would set it up. So that tells you how much aluminum you've made. Of course, they could have made this into a full problem if they had given us an electric current and a time, but oh well. I think the next problem might involve that. How long would it take to reduce 1 mole of each of the following ions using the current indicated? So we've got, well, I already did aluminum, so let's pass on it. Let's do gold. Let's do part D. So we've got a current of 3.57 amperes, or coulombs per second in other words, and you've got gold, gold 3 to be specific, which requires 3 moles of electrons per mole of gold. Okay, let's see what we can do with this. So we need to figure out how much time it'll take. I know that, and it's just 1 mole. Okay, so if I've got exactly 1 mole of gold 3 ion, or solid gold, however you want to write it, it's not really of that much consequence. Maybe write it with the charge so that it's easy to remember how many moles of electrons you need. Let's see, every 1 mole of gold ion requires 3 moles of electrons, and every 1 mole of electrons requires 96,485 coulombs of charge. And then based on the electric current that was given, 3.57 amperes, it looks like every 3.57 coulombs of charge take 1 second to be pumped into the system. Yeah, every 1 second you get 3.57 coulombs of charge, so you can calculate the total seconds, and we'll probably need to convert this to minutes or even hours, so let's go ahead and set that up. 60 seconds is 1 minute, and perhaps 60 minutes. Okay, this marker's about dead. 60 minutes is 1 hour. Okay, I'll calculate up to here, and then if it's not a reasonable number of seconds, then we'll go to minutes, and if it's not a reasonable number of minutes, we'll go to hours. Let's see, so that's 1 times 3 times 96,485 over 3.57. 96,485 over 3.57, and multiplying that by 3. Okay, yeah, that's a lot of seconds. So that's 811, or no, wait, 81,100 seconds. Yeah, 81,100 seconds, and then 81,100 divided by, I'm just going to go ahead and go straight to hours, so divide by 3,600, and that's 22.5 hours. That's going to take 22.5 hours. 22.5 hours to put out 1 mole of gold. And 1 mole of gold is how many grams? Molar mass of gold is 196.967. That's 196.967 grams of gold. So, yeah, that's basically how these problems go. It's not that hard to understand them once you've practiced enough of them. Is there anything else worth going over here? 48, a current of 2.345 amperes passes through the cell shown in figure 19. Is that the one with the chlorine and... No, it's a different one. Okay, I don't have it. Anyway, it passes through the cell for 45 minutes. What's the volume of the hydrogen collected at room temperature? If the pressure is exactly 1 atmosphere. Hint, is hydrogen the only gas present above the water? What is the volume of the hydrogen collected at room temperature if the pressure is exactly 1 atmosphere? Well, if we know the temperature and we know the pressure, then all you have to do is solve for the moles of hydrogen, and then you'll plug that into the ideal gas equation to get the volume. So I'm not sure what's confusing me is the hint. It feels unnecessary. Okay, it's whatever. Well, let's at least set this up. So even without seeing their diagram, it's not that hard to figure out what they want you to do. So we've got, you would take hydrogen ion, 2 moles of hydrogen ion react with 2 moles of electrons to produce 1 mole of hydrogen gas. So then you can calculate if it's 2.345 amperes for 45 minutes. Then start with your 45 minutes. Start with your 45 minutes, convert it to seconds. Okay, so 45 minutes, convert every 1 minute is 60 seconds. I don't know if they mean for the 45 to be an exact number. And then for every 1 second, they told us it was 2.345 amperes, so 2.345 coulombs of charge per second. And then, of course, Faraday's constant, 96,485 coulombs for every 1 mole of electrons. And of course, we've got 2 moles of electrons for every 1 mole of hydrogen gas. And that gives you your moles of hydrogen gas. And then ideal gas equation, PV equals nRT. R would be 0.08206 liter atmospheres per mole kelvins. Pressure is exactly 1 atmosphere. So, yeah, the rest you can take care of from there. V equals nRT over P. Convert your temperature to kelvins if it's not in kelvins already. They said room temperature, so 298 kelvins, and there you go. 49. An irregularly shaped metal part made from a particular alloy was galvanized with zinc using a zinc nitrate solution. When a current of 2.599 amperes was used, it took exactly 1 hour to deposit a 0.01123 millimeter layer of zinc on the part. What was the total surface area of the part? The density of zinc is 7.140 grams per cubic centimeter. Okay, that's a bit more advanced than what we usually see for electrolysis problems. So this problem is talking about one of the applications of electrolysis, which is called electroplating. Basically, if you want to cover something in a layer of metal, then a nice way to do it smoothly is to dip the material that you want to cover in a solution containing ions of that metal and connect it to a battery and effectively turn it into one of the electrodes of an electrolytic cell. So, for example, if I was in the business of making silverware, and I didn't want to make my spoons out of pure silver, I didn't want to make my spoons 100% silver because silver is expensive, then something I could do is I could take my spoon, so here's my best attempt at drawing a spoon, made of cheaper metals, and plug it into a battery. Let's see, I would want to plug it into the negative end of the battery, or whatever my electricity source is. And then over here I'll just have, a normal electrode. And yeah, dip that in a solution that contains silver ions. So there's silver ions floating around and whatever else goes with it. Not chloride, nitrate. Something that's soluble with silver. And yeah, the silver ions would get attracted to the spoon, so maybe the spoon is made out of something relatively cheap, like iron or steel or something like that, and I want to apply just a coat of silver onto the surface. Instead of making the whole spoon out of silver, just get a layer of silver to deposit on top of it. I can use electrolysis to do that. That process is called electroplating. Electroplating. And that's what's described in problem 49. So we have an irregularly shaped metal part, and we want to apply a layer of zinc onto it. So we know the amperage, we know the electric current, we know the amount of time it took. They said exactly 1 hour. So knowing that, and knowing the fact that it's zinc, we can already figure out how much zinc was applied. That's not too different from what we've done before. It's essentially the same as what we did with problem 48, except you take the extra step after calculating the moles. You multiply by molar mass to get the grams of zinc. And then once you've got your grams of zinc, you can use the density, 7.140 grams per cubic centimeter, to get the volume in cubic centimeters. And volume is going to equal the area of the base times the height, or in this case, the surface area times the thickness, in other words. So yeah, once you've got the volume in cubic centimeters, convert your thickness, which is given in millimeters, convert that to centimeters, and volume divided by thickness gives you surface area. So I think with that description, you can take it from there. And yeah, I guess that's it for this chapter. So another shorter than average video, and I'm thinking maybe the next video might also be shorter than average because nuclear chemistry is also relatively easy. Maybe I'll make up for it in the organic chemistry video, but that's it for tonight. This has been Al the Tutor, reminding you once again that ignorance is not bliss. Take care, and I will see you in the next video.